Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics within the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, a lot of the cool stuff happening inside the universe. I love being a scientist. I love getting to work on these amazing topics, and I really love chatting to everybody about all of the cool things I get to research. I see some of the regulars already coming in. We have David, Scott, Paul. Hi, great to see you. As always, great to see all the regulars coming in. If you haven't done so already, welcome if you're a new viewer. If you haven't done so already, please do like this video, subscribe, leave a comment, do all of the usual YouTube stuff. It really is the best way to support what I do here. So please do boost the engagement, do all of the usual YouTube things. You know how YouTube works. Press buttons, make stuff happen. Hey, Nina, great to see you in one of the live streams. And Mita, nice to see you as well. Paul, you come here, you don't just come here for the cool sweatshirts. Well, I'm glad you like the cool sweatshirts. This is a Quizkazact sweatshirt, hoodie. Quizkazact is another YouTube channel that does science outreach. I'm in no way promoting, this is not a paid ad. I just love Quizkazact. I think they're a great channel. The second favorite YouTube channel, obviously my favorite YouTube channel is Cup of Cosmology. And I know it's your favorite one as well, else you wouldn't be here. So if you haven't done so yet, do all of the usual YouTube stuff. So for anyone who doesn't know, this is an interactive stream. The idea here is that you people can ask me anything you want about space, about time, about cosmology, about academia, about science, about myself. You can literally ask me anything you want and I will try my best to answer. As always, I won't necessarily have all of the answers to all of your questions, but I will do my best to answer the questions that I do know the answers to, and those that I don't will either figure it out as we go or write it down on my list and then never look at that list again. That's usually how these things happen. So, as always, feel free to ask me whatever you want about space, about time, about cosmology, usual stuff. You can ask me whatever you want. To anybody watching on Twitch, hello to the Twitch viewers as well. I know I usually monopolize the YouTube viewers, but to anybody watching on Twitch, please welcome. I just pressed a button and something appeared on screen. I forgot that that's what happens when I press a button, so apologies if you just saw a random thing flash up on screen. I just found a button. I was like, what does that do? Oh yeah, that puts a chat on the screen. So whichever platform you're watching on, welcome. Great to have you here. And for anyone who doesn't know, do all of the YouTube. I've already said that. Anyway, great to have everybody here. So last week I was not online. The reason being I was just not feeling well. So I took the Sunday off. I took the whole weekend off. I basically built a blanket for it and spent most of my weekend last weekend in a blanket for it. Excellent life choice. I very much recommend everybody doing blanket for it. It is a good life choice. And just brief announcements. Next week, there won't be a Cup of Cosmology. Next week is Easter Sunday. I am actually traveling. I leave on my travels tomorrow. So I have to do a few hours work in the morning, which honestly, no work is going to happen. But I do a few hours work tomorrow morning, and then I leave for my holiday in the middle of the day. And I'm super excited, and I'm going to have, the plan is 2 weeks with no work. We'll see how that goes. I'm usually extremely bad at keeping myself away from work, but this time I am on doctor's orders to have therapist orders to have 2 weeks completely away from work. So there won't be a stream next weekend because hopefully I'll be doing absolutely nothing. We'll see how that goes. I'm not one for doing nothing when traveling, but we'll see. There will definitely not be an April Fool's broadcast. Also, incidentally, I am not a huge fan of April Fool's. I don't like that it's a day where people just feel like they can lie to you. I like people being honest. And, especially what annoys me on April Fools is when you get respectable sources participating, like news channels, or what personally annoys me, the sites where we put our papers. Some people write like joking papers, and you're never sure if you're reading a real scientific paper or a mock one. And I feel like science should always, be held to the standard where you expect it to be reliable. So I'm not a huge fan of April Fools. I feel like places like news sites and journals should not really lie to you. And April Fools is a day where everyone just lies to you about everything. Not a huge fan personally, but if anyone wants to celebrate it, go ahead. But yes, there will not be an April Fools broadcast on my behalf, not because it's April Fools, just because I'm busy traveling. But yes, not a huge fan of April Fools. Okay, I see a long comment here. Read something recently about self-interacting dark matter, how it might explain where dark matter seems to be in galaxies. Also, that matter and dark matter may have appeared at different times. Did you ask me that last week? I feel like I remember seeing self-interacting dark matter quite recently, And I don't think I answered that question. So did you ask that last week and I ignored you? Anyway, self-interacting dark matter, I'll get to that in one sec. Self-interacting dark matter is a very interesting thing to talk about. I'll get to that in one sec. Just want to answer some more comments here from Nina. You hate April Fools, everyone lies and you can't believe anything anyone tells you. Yeah, I agree. Definitely a neurotypical thing. As someone who is not neurotypical, I don't appreciate it being lied to on purpose. Yes. Yeah, if you find dark matter, make sure that the paper isn't published on April 1st. Yeah, see, this is the thing. Because we know that there are a lot of jokey papers on April 1st, a lot of scientists actually hold off on publishing on April 1st because, it's a day where you can't really believe anything. So why would you publish a scientific result on a day where people might not take you seriously? Right, you did ask me on Mastodon. Yes, that is where you mentioned self-interacting dark matter, and I said I'd be happy to talk about that. Yes, that's where you mentioned it. Great. Yes, for anyone who doesn't follow me on Mastodon, you're welcome to follow me on Mastodon. My username is dchooper91_Cosmo, and I post outreach stuff, not frequently. I have a second personal account, which you're also welcome to follow, but be warned that it contains a lot of non-science shitposting. But feel free to follow me on Mastodon. As people know by now, I'm no longer active on Twitter. Okay, just want to address this comment from Ben before we move on to self-interacting dark matter, of what would today's cosmology look like if Leavitt didn't discover the correlation between period and luminosity. So the correlation between period and luminosity, as the name implies, is this link that we have between bright objects and how frequently we can see Cepheid stars. It is Cepheid stars, yes. So how bright they are versus their period. So it's something that we can use as kind of a cosmic lighthouse, and it allows us to measure distances in the universe. So I just want to point out that it wasn't just Leavitt who discovered this. There was, yes, it was, yes, Henrietta Swan Leavitt, yes. It's a very cool thing, but I think it's a very useful discovery, and it really has helped us measure a lot of distances and a lot of things in the universe, mainly because if you can measure distance, you can figure out how things are moving, how things are evolving. Things like dark energy we know of because we can measure how fast galaxies are moving away from us, and for this we need some type of anchor, and Cepheids provide a good anchor for this. However, I do not believe that science is a result of individual geniuses. I believe that science is the gradual progress, and it's something that is a team effort. So while I think Henrietta Swan Leavitt deserves a lot of credit for discovering this relationship, and it was a very cool piece of work, honestly, I think if she hadn't discovered it, someone else would have done. I think this is true for most of the science that we have today. If one person hadn't found it, somebody else would have done. You have some very random accidental discoveries like penicillin. That was a complete fluke, but very, very cool one. But I feel like a lot of things, if it weren't one person, it would be somebody else, because that's kind of how things work. So yes, Henrietta Swan Leavitt found the correlation between period and luminosity, amazing piece of work. But to answer your question, what would today's cosmology look like if she hadn't discovered that? I think somebody else would have discovered that. And the thing is, it's it's an observation that other people were doing at the same time. Other people will be interested in it as well. So I do think it's something that would have been discovered anyway. She got there first. That is amazing, of course. But yes, I always do believe that science is not contingent on one single person, but rather it is a process. So if it weren't one person discovering it, then it would have been somebody else. And I know that's not the answer you were hoping for. Okay, so I see we have the very cool question about the death of the universes. Sorry, the death of the universe. And I love talking about that. I did a whole stream about the eventual fate of the universe, so we are going to get back to that. But let's talk about self-interacting dark matter. So first of all, let's just recap. What is dark matter? Does dark matter have interaction? What is self-interacting dark matter? Why should we care? So the universe has three main components: everything we see, everything we're accustomed to, everything from me to my tea mug to the pen I just threw on the table. This is normal matter, and normal matter is only 5% of the energy budget of the observable universe. There's another 26.2%, which is in the form of dark matter. So dark matter is this weird type of matter that interacts via the gravitational force, but doesn't interact electromagnetically. This means that dark matter is essentially invisible. It does not emit light, it does not absorb light, it does not reflect light in any way. Therefore, as far as light is concerned, dark matter is not there. However, due to its gravitational effects, we can figure out that there must be something there that we can't see that behaves like matter, and this is what we call dark matter. The remaining 69% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. How do we know this? Where do these numbers come from? Well, the biggest piece of evidence we have for these numbers comes from the cosmic microwave background radiation. 11 minutes for anyone keeping track. Cosmic microwave background radiation is the oldest light we can see in the universe. It is the background light behind everything else in the cosmos. No matter where you look in the night sky, the CMB, the cosmic microwave background radiation, is there behind everything else. You can see here there are tiny, tiny, tiny temperature differences. We have some regions of this map that is blue, some regions that are more orange. This corresponds to photons, particles of light that were slightly more or less energetic in the early universe. Very, very tiny differences. And by studying the statistical properties of this image, like how many blue blobs are there, how big are the blue blobs, how many orange blobs are there, how big are the orange blobs, by answering these questions, we can get a snapshot of what the baby universe looked like and a snapshot of what the universe, we can project that forward to what the universe looks like today. So we can use the cosmic microwave background radiation to get this cosmic pie chart here with these numbers. Okay, so that's just brief recap. Anyone who's seen this stream frequently knows that this is a usual recap. So what do we know about dark matter? Well, we know it doesn't interact with light, and we know it does interact with gravity. Strong and weak force are up for debate. Probably has weak interactions, maybe. So 4 forces govern the universe. Electromagnetic, we're used to this. Electricity, magnetism. Gravity keeps us in orbit around planet, around stars. I drop pen falls down. Gravity. Strong nuclear force binds everything together at the atomic scale. And weak nuclear force is responsible for radioactive decay. Now, of these, we have pretty good understanding of 3 of them. The one we don't understand is gravity. But dark matter is something that interacts via the gravitational force. It bends space-time, and objects move according to the curvature of space-time. So dark matter has mass, it bends space-time, but it does not interact via the electromagnetic force. So one thing we usually say about dark matter is it is cold and collisionless. Collisionless means it doesn't bump into other particles, because it can't bump into photons, for example, because this would mean interacting via the electromagnetic force, which it doesn't do. It can't bump into other particles too much, because this would involve one of the other forces, which it doesn't really do. So we say that dark matter doesn't really interact with much. We think in the very early universe it might have talked to normal matter, and then it broke away as the universe cooled down. So this means that dark matter is collisionless. And what do we mean when we say dark matter is cold? So when we say dark matter is cold, we're talking about its mass, or how heavy dark matter is. Every particle in the universe has mass, and depending on this mass, it moves at a different speed. For an example, photons, particles of light, have no mass, and they can travel at the speed of light. Neutrinos have tiny, 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 tiny mass, travel almost at the speed of light. So when we say that dark matter is cold, we're basically saying that it moves quite slowly. How do we know this? We know this by looking at galaxies. If dark matter were moving quickly, it wouldn't have time to settle down and produce galaxies. So galaxies form when you have a lot of dark matter, and then kind of the hydrogen and the stars coalesce or collapse on top of this dark matter, form around this dark matter. So dark matter provides a scaffolding for galaxies. This means that dark matter needs to be moving slowly. If dark matter were moving quickly, it would be too quick to actually allow these galaxies to form, because it would just be whipping through the universe. So based on the amount of galaxies we say that dark matter is cold and collisionless, because we know that it's not interacting with other particles. If dark matter were interacting with other particles at the time, for an example, when the cosmic microwave background radiation was produced, we would see it here. According to this map here, dark matter does not really talk to anything else. So we have dark matter that is cold, that is collisionless. This is the standard model of dark matter, but we have not found the standard model. We have not found standard dark matter, despite a lot of people searching for it. There are different ways we can search for dark matter, and we haven't found it yet. We just know it should be there from cosmology, but we haven't actually gone like, haha, dark matter, I see you, I see what you are. We're still trying to do that. So this means that because we haven't found it yet, there is a motivation to look at other types of dark matter that are not just cold and not just collisionless. Collisionless, lack of collisions, lack of bumping into other things. So if we want to go and look at different types of dark matter, things we can do is give dark matter a small amount of conversation with normal particles, make dark matter bump into things, make dark matter talk to things, but only a small amount. Because if dark matter does this too much, we would have seen it already. Something else we can do is change the mass. We could make dark matter maybe slightly heavier and therefore slightly slower, or we could make dark matter slightly lighter and therefore slightly faster, with the constraints that we need to be able to form galaxies. So a lot of what people do with dark matter is what is known as model building, where you build a model of dark matter that can still explain the universe as we see it, but that might explain why we haven't found it yet. And this is a lot of what I've done during my PhD and during my first postdoc, was also asking this question of what can I do to dark matter to make it more interesting than normal dark matter, and also explain why we haven't seen it yet and how would we see it. Things like making it slightly faster but not enough to knock out galaxies, making it half of dark matter cold so it can form galaxies and half of dark matter warm so it doesn't form galaxies, then you have a nice balance. One very interesting idea in this direction, so I mentioned dark matter does not interact with anything in normal matter. So then there's a fun question of, does dark matter interact with itself? Can we have self-interacting dark matter? So dark matter that interacts with itself. This is what is known as self-interacting dark matter. Now, this is a very cool thing to ask because we know that normal matter does interact with itself, right? We can form atoms, we can form molecules, we can form structures. Can we do the same in dark matter? Now, you just want to make a comment here that you can form different types of objects without this specific self-interaction. But the question of, can dark matter interact with itself and what would this look like? And then there's different ways you can make this happen. But anytime you have two particles interacting, what usually happens is there is a force that mediates this, a force that explains this. You know, when we see light, there is the electromagnetic force. When two particles bump into each other, usually they get very close, there's some interaction, and then they come away. And this interaction is governed by the forces. So then if we have self-interacting dark matter, we're talking about dark matter that doesn't just interact via gravity, but that there would be some type of hidden force in the dark sector, which would explain how dark matter could interact with itself. So is self-interacting dark matter interesting? Why should we care? Glad you asked these questions. I know you didn't, but self-interacting dark matter was the prompt and we're just running with it. Now, I feel like these streams have a lot of improv to them. You give me a prompt and I just see how far I can go with the prompt, and I love it. I love this format. It very much works for how my brain processes things. So I should drink more. I'm talking quick. If people think I'm talking quickly, let me know and I will try to slow down. I feel like I might be talking a bit faster than usual, but less than I did in the early Periscope days where I spoke way too quickly. So I have calmed down a bit since then. So different reasons why we might be interested in self-interacting dark matter. From a model building perspective, where we just mentioned, where we build models of dark matter, we come up with new ideas for dark matter. Self-interacting dark matter kind of makes sense. Why wouldn't it talk to itself? It's the first logical thing to think of, or it's a very logical thing to think of. And one very big reason why we're interested in self-interacting dark matter is because there's a couple of issues. When, dark matter is the best thing we have to explain things like the cosmic microwave background radiation, or why galaxies look the way they do. But not everything is solved in cosmology. Not everything has a clear explanation. And there is something that is known as a small-scale crisis. So when we want to study what would dark matter behave, we ask the question of what would dark matter look like in the universe? We can't see it, but what would it do? And to answer this question, you run a simulation. So you basically construct a box on your computer. In this box, you put everything you know about dark matter and the laws of physics. And you say, okay, I start with this much dark matter evenly distributed throughout my box. This is a pretty good replication of what would happen in the universe. And you press play. And then you see if you form galaxies, if you form structures, what dark matter does if it's in a box obeying the laws of physics. Because we can't actually take a box of the universe and put it in our lab, this is how we do it. We need a pretty big box. So instead, we run a simulation where we say, simulate billions of galaxies and show me what happens. And if you do this on the scales of galaxies, so you put your simulation where you expect to get, 100 galaxies, 200 galaxies by the end, and you run this, and then you see what dark matter or what the universe in your box looks like. And then you can compare this to what we actually see. And this is something that we do a lot in cosmology because we can't pull the universe down and put it on a lab table. We simulate it with everything we think we know about dark matter, and then we can compare what we simulated with what we're seeing. Yes, we're going to need a bigger box. Very famous. I don't think they were using boxes, but yeah, we're going to need a bigger box. So we simulate the universe and then we compare. And when we do this, not everything matches. There are simulations of the universe. When we look on small scales, on scales of a couple galaxies, what we simulate and what we observe doesn't completely match. Assuming if you put in your box dark matter that is cold and not bumping into anything, you don't completely get what we see. So there are a couple of key differences. The first one is what is known as the missing satellite problem, where in our simulations, we expect more satellites around galaxies like the Milky Way. And then when we look around the Milky Way, we don't see as many satellites as our box tells us we should see. This is quite a controversial one because maybe our galaxy just doesn't have satellites. Maybe we just don't see them. And is this really a crisis just because our simulation says there should be 10 satellites and we've observed 5? Is this a problem? But then there's another couple of problems, and one of them is how dark matter is distributed in galaxies. Our simulations show that it should be, if you imagine that a galaxy, we all think of a galaxy as like a disk. This is our galaxy, right? It's a disk. But what our galaxy actually has is a big ball of dark matter around it. So there's the visible galaxy, I'm looking at it edge on. You have the galaxy here, and what you actually have around it is a big ball of dark matter. So you have big ball of dark matter with galaxy, the visible part of galaxy flat in the middle, whichever angle you want to look at it from. You have the galactic disk, which is the visible part, and the halo of dark matter kind of everywhere around it. But the way this dark matter is distributed, is there more of it at the center of the galaxy? Is it evenly spread out? Does it fall off sharply? Does it gradually go out? What we get out of our box and what we see in the universe is slightly different. So it seems like our box expects there to be a lot of differences, a lot of different ways that following approximately the same pattern, but different ways that dark matter can spread out inside these galaxies. However, when we observe the galaxies around us, the dark matter appears to be pretty similar. So I just talked about two problems together. One is the core cusps, where the galaxies are cored with all the dark matter at the center, or cusps where they fall off evenly. And something known as a diversity problem. Physics does have many diversity problems, but one of them in cosmology is this fact that our simulations expect there to be a big range of the way that dark matter can fall off in galaxies, but we don't really observe this. So you have these problems: missing satellites, diversity problem, core cusp, and another one that is called too big to fail, which is very much related to the missing satellite one, where there should be galaxies that we should see. Based on their size, they should have ignited, and yet we don't see them in a specific size range. So these 4 problems, there's a lot of different ways you can go about trying to solve them. Now, just a reminder, in our box, for now, I put only cold dark matter. So one direction here, say, okay, we only put dark matter, but what about normal matter? Is this going to affect it? Now, the reason we only put dark matter in our box is because dark matter is 5 times more massive than normal matter. And putting normal matter in, then you have things like friction, you have heating, you have different effects to consider, and it's a bit harder to simulate. Is it enough if we put normal matter in our box to explain these differences? It seems like the answer is no. Some people say maybe, but it very much seems that even if you put normal matter in your box together with cold dark matter, you can't really explain the small scale issues that we have, these small scale issues. And this is what is known as a small scale crisis. Let's go back to self-interacting dark matter. If you take your box and you run it again, but now you allow the dark matter to talk to itself, you allow dark matter to bump into itself, you allow self-interacting dark matter, then what you get out looks a bit closer to what we actually see in the galaxies around us. It's not perfect. Then you have to play about with how much dark matter can talk to itself. What can dark matter actually do? How much self-interaction do we want with things here? But it does seem like putting self-interacting dark matter inside our box gives a slightly better fit or a slightly better resemblance to what the universe actually looks like. So this is why self-interacting dark matter is extremely interesting. So the initial question by David Howden quite some time ago by now was, you read something recently about self-interacting dark matter, how it might explain where dark matter seems to be in galaxies, also that matter and dark matter may have appeared at different times. So if we put self-interacting dark matter into our simulations, we can explain a bit better why galaxies look the way they do. However, this is not really enough to say this is self-interacting dark matter, because there needs to be a stronger evidence for this in general. Now, the problem with these simulations is it's very, very messy. There's a lot of stuff that is very difficult to understand, which means there's a lot of uncertainty in the simulation. For an example, how much do we need to care about the temperature of the intergalactic medium, the space in between galaxies? How much do we need to care about normal matter heating up and reacting with itself as well? So while self-interacting dark matter seems to do a better job in this context, it's still not really enough to go out there and say self-interacting dark matter is the solution. It just seems to be a bit better at explaining this small-scale crisis. But also, small-scale crisis is often put in quotation marks because some people are like, well, it's just going to be astrophysics. Just put your normal matter in and everything solves. So it's not on the same scale as some of the other crises we have in cosmology, but it is a very interesting one. And self-interacting dark matter does seem to get us one step closer to explaining this. So that is very, very cool. And another very cool thing is then you need to ask the question, going back to the model building perspective, of how do you form self-interacting dark matter? Would it form at the same time as normal matter? And people have come up with different mechanisms where you could form normal matter, and then a bit later or a bit earlier, you form the self-interacting dark matter. If you have self-interactions with dark matter, I mentioned before that we believe that in the very early universe, dark matter and normal matter did actually talk to each other somewhat. Right? They did talk to each other somewhat. And then they broke away. As the universe cooled down, dark matter kind of fell out and stopped talking to everything else. Now, if you put self-interacting dark matter, the dark matter would actually fall out at a different time, because it has its own interactions. It's kind of got its own click going there, so it doesn't need to talk to the rest. So then it changes the time at which dark matter breaks away. So self-interacting dark matter is really, really interesting. And then you can take it one step further and you can have fun things like, what type of interactions are we talking about here? Is it just that dark matter is bumping into itself? Is dark matter annihilating in the same way we have matter and antimatter that can annihilate? Are we talking here about having dark matter and anti-dark matter that are annihilating? Or could we have a very cool thing that is known as cannibal dark matter, where you have 3 dark matter particles go in and only 2 come out? And this is a very fun model because the dark matter basically cannibalizes itself. And this is very good because it gives you a way to get rid of some excess dark matter. And if you have too much dark matter, it gives you a way to get rid of it. And it has very fun behavior. And I actually studied it's cannibal dark matter at some point during my PhD. It was a really fun side project I did. It was really, really interesting model. And it's really interesting to think of all the different ways you can make dark matter interact with itself. So that was a very long answer. The question was, is self-interacting dark matter interesting? Yes, it is. Can it explain why galaxies look the way they do? Maybe. Is it the right model of dark matter? We don't know. That's the short summary version there. But personally, I think self-interacting dark matter is very, very cool. I have not yet worked on it myself. Fun fact, I have actually had an idea for a project on self-interacting dark matter for about 6 years now. And I have not yet done this. And I know it's been so long because every time I apply for postdocs or for the next position, you have to write something in there about what you're going to work on, your research plan. And already when I did my first round of postdoc applications, which was 2018, I wrote a paragraph about, I want to do this thing with self-interacting dark matter. And then I was very busy during my first postdoc. I didn't have time to do it. And when I applied for the second round of postdocs, I also had this in my research plan. If I'm going to do this thing with self-interacting dark matter, and here's why. And I still haven't done it. So yeah, I wrote this for the first time in 2018, and I still haven't done it. By now, someone has done something very similar to what I wanted to do, obviously, because someone else is always going to do it if you don't get there first. But I still do have an idea of something I could do with self-interacting dark matter. And yeah, maybe someday. It was incidentally also in some of my grant proposals. It's still there. I have this paragraph that's like 6 years old. It's like, I'm promised to do this. And it hasn't happened yet. So Yes, self-interacting dark matter is very cool. Thank you for that question. This was a very long answer. I like it when I can go really in depth in a topic. Self-interacting dark matter is a really specialized question. Sometimes on the stream I get questions like, "What is dark matter?" which is a perfectly valid question, especially if it's your first time here. I always try to review things because I don't expect that people have seen all of my other streams. But your question of self-interacting dark matter, David, was very in depth, and that means that it really allows me to jump into how we do dark matter research. The simulation in a box. This is not just for self-interacting dark matter. This is what we do for any type of dark matter. Really, is you just make a box, you put stuff in a box on your computer, you run your computer, and then you find that you put something wrong, and you do this for about 5 years until you've eventually fixed your code. If you're wondering where that comment came from, it's because I'm working on a project that we wanted to be done with last year. And every time we say, okay, this is the final thing, this is the final piece that was missing, we run a bunch of simulations and then we find another mistake. And we've done this so many times, and it's something that we really wanted finished. And I'm currently a bit annoyed that we haven't finished this yet. Yesterday evening, I did a very bad thing. So I very much, just going to be clear here, I do not condone working on weekends. I do not condone working overtime. There is a problem in academia of people working overtime and glorifying it like, hey, I did 60 hours this weekend. So cool. No, you have time management issues. So bearing in mind that I very much do not endorse what I'm about to say, but I'm a hypocrite. And yesterday at 9 p.m., there was something buzzing in my brain. And I was just like, I have a suspicion that there's something about an equation that is bothering me. One equation in this paper that we're trying to finish is bothering me. So my idea at 9 p.m. yesterday evening was, I'll just look at the equation, convince myself that it's correct, and move on with my Saturday evening. It will be 10 minutes. 3 hours later, so at midnight, I was convinced that our equation is wrong. So yes, anyway, I know how to fix it. It's just another setback. So if I make comments like when I just made the comment of you run your simulation again, and then again, this is part of the process. This is part of science, and this is the context for why I just made this comment. But on the plus side, I'm one step closer to having the right answer. And again, I do not condone working at midnight on a Saturday. I do not do this often. Sometimes you just have that bug in your brain and you have to check. And it turns out the bug wasn't in my brain. The bug was in the project. But we know how to solve it. So again, I do not condone people working midnight on Saturdays. I do it occasionally, but I am taking time off during the week to compensate. 2 weeks off, as I mentioned, 2 weeks off of work. Well, a week and 4 days off of work starting tomorrow. Okay, just went on a random tangent there to tell you about this thing because it's part of the process. Actually, before I go into the end of the universe that Nina asked about some time ago, I just want to make a comment that being a scientist is amazing. Being a scientist is really fun, but there are ups and downs, as there are with any job. And sometimes the ups and the downs, you hope that the good days compensate for the bad days. It isn't always the case. So going to be completely honest with everybody because I always do talk honestly about these things. I have been struggling with my mental health and work-related topics for the last few weeks. I'm doing okay. Please do not worry. I'm okay. But I'm in one of the down periods in terms of science. And in fact, I wanted to do it today, but then didn't have time. So didn't have time to plan it. But I'm going to do a stream soon with the title of The Ups and Downs of Academia, where I'm going to talk about what it's like, what it's like to be a scientist, the ups and the downs, the good and the bad, and why we still do it and why we love doing it despite the downs. So probably either in 2 weeks, like the next stream, because I'm not doing one next week, probably in 2 weeks, I'm going to do a stream about the ups and downs of academia. Yeah, that's going to be fun. So stay tuned for that. Okay, your job had 50 hours mandatory per week. Yeah, that is illegal. So I know some companies do it, but that is actually illegal. And you know what you should do if your company's forcing you to work overtime? You should unionize. Join a union. If you can't join a union, unionize. Get all your co-workers together because there are more of you than there are of management. And I believe that every worker should be part of a union. I am part of a union, obviously. I believe that everyone should be part of a union because unions are the best way to actually fight for better working conditions. And if your company is making 50 hours mandatory, it is illegal. It is against the law. nobody's stopping them. But if you unionize and you all go on strike, there are more of you than there are of them. It is not illegal in America. Yeah, there's some dodgy ways they can get around it. Some contracts that are like, well, it's overtime. So, it's not, you get compensation for working overtime. Do not believe it. Do not believe it. Unionize. My piece of advice to anyone, whatever country you're in, whatever job you're in, unionize. Unionizing is always a good option. So thank you for your nice comment there, Paul. And just to say that Cup of Cosmology is always one of the positives. And even on days when I'm struggling with academia, with science, coming on Cup of Cosmology is actually a way to make me remember why I like science so much and why I like doing this, because telling people about the amazing things I get to work on is really, really cool. And it's always been my favorite part of my job is teaching and talking to people about the research I get to do, going to conferences and meeting people. Again, I'm going to do a whole stream about this. But Cup of Cosmology is always a constant source of positivity for me. And when I feel like it's not going to be, I don't do a stream, because I've always said that Cup of Cosmology should never feel like an obligation to me or to hopefully any of you turning up here every week. So yes, thank you for your comment, Paul. It's very nice of you. And yes, Cup of Cosmology is one of my positives, and it is something that really has helped me a lot during my time in academia. So yes, thank you for that very nice comment. Okay, before I go into a whole lot of tangent about unionizing, I just did the small version, but please do unionize and rise up against your evil management, because there are more of you than there are of them. Now let's get into the death of the universe. I'm just going to scroll back and read the question. My tea is currently at optimum temperature, so give me a chance to catch my breath while you all think about how to join a union, and then we're going to go into death of the universe. Jumping from one fun topic to the next. Okay, the question by Nina. The universe is expanding until the heat death. There's also the idea that the universe might contract again at some point, resulting in another Big Bang. I hope it's the second one. Heat death is too depressing. Okay, so, comment about union. Let me just read your union comment. Endorse that. Do unionize if you can. It's not that easy in all countries. I agree. There are hurdles to unionizing. It is not as easy as it should be. Please do it anyway, if you can. Be active in your union. I agree. I really value being able to help my members as I lay rep for my union. That is great, David. I'm very glad you are helping out in your union. I very much endorse this. This is a great thing to do. Please do more of that. We need more union people. Excellent. Good thing. Okay. So the universe is currently expanding. This expansion, the universe is growing. Things are moving further and further away from other things. So then there's a question of, is it always going to do this? What is going to happen? Basically, how is the universe going to end? I'm going to talk about 4 possible scenarios, 4 possible ways the universe can end. And for this, I need to bring up one of my favorite images, which has a nickname, which I'm not going to mention here, because despite what it may seem, this is a PG-13 show. Hey, David, great to see you here. Unions are important and good. Need to make sure young realize value of unions. Great, love that comment. Yes, and thank you for your emails, David. I did answer you today. I have answered your emails finally. I know you've been waiting for 2 weeks. I finally got around to answering your emails. Okay, let's talk about history of the universe and future of the universe. So, at some point, there was something. In the beginning, there was something. We don't know what this something was, but this something expanded. This expansion has been going on ever since, and today it is still ongoing. So, possible things that could happen. Now, for a lot of time, people believed that one possible end of the universe that for a lot of years seemed quite plausible. Lol on nickname, yes. Yes, people, if you know the nickname of that image, and I'm not going to repeat it out loud because this is a PG-13 show. Sometimes, I do slip up very frequently. And there is always a heavy dose of innuendo, because that's just who I am. Okay, so the universe is expanding. From one idea of a potential end of the universe is that this expansion at some point would stop and collapse. Now, the reason for this is because you can imagine the universe is filled with a lot of things, a lot of matter. All of this matter creates a gravitational attraction, so it pulls things together. So if you imagine you had this initial expansion, and the expansion at some point should slow down, right? It runs out of steam, the expansion should stop. Once it stops, Gravity should take over and pull everything back down. This means that instead of expanding, at some point the universe would stop expanding and contract upon itself. It would go contract back down to a big ball or to a small ball. Then you'd have a lot of mass, a lot of energy condensed into a small point. This would basically replicate the conditions of the first Big Bang, and then this would expand again. And this leads to an idea of a cyclical universe, a universe that is expanding and contracting, expanding and contracting. And this is kind of a nice scenario to think about, right? Because it gives a sense of continuity. The universe expands, it slows down, it collapses, it does this again. You have this kind of breathing universe, right? It's kind of nice to think about. Unfortunately, the universe does not care about our preferences in any way. And this idea of a collapsing universe, which is known as the Big Crunch, because you start with the Big Bang, then the Big Crunch, and so on, this idea actually doesn't seem like the most likely option anymore. The reason is because not only is the universe expanding, but this expansion is accelerating. If I go back to my history of the universe map, and I'm actually going to change to this one instead here. Oh, did not mean to maximize that, just meant to put it there. Why did that maximize? Press the wrong button, here we go. Okay, so you can see that at some point there is this comment towards the right side that says dark energy accelerated expansion. So the universe not only is expanding, but this expansion is speeding up. So the universe is expanding faster today than it was in the past. Our best explanation for this is dark energy. Dark energy, as I mentioned before, is this weird type of energy that accounts for 70% of the energy budget of the universe, and which is pushing things outwards. Right, yes, thank you for calling me out on that poll. I said it would contract to a small ball, but this puts a size on the universe. And we can't actually quantify the size of the universe because the universe is infinite. So talking in terms of density, it would be a very, very dense ball, but saying a small ball is wrong or a big ball is wrong because we can't quantify the size of the universe. Thank you for calling me out on that poll. Yes, so the idea of the cyclical universe is started as a big something, expanded into an infinitely big something, will go back to being smaller, collapse, and then smaller than it is now, but still infinitely big, and then it would expand again. But we have found that the universe is currently dominated by dark energy, and this dark energy is making the universe expand faster today than it was in the past. Which means if the expansion is speeding up, it's quite unlikely that at some point it's going to stop and go the other way, because it's still going, it's getting faster. Things are moving away faster than they were in the past because dark energy is pushing everything outwards. So with this, the idea of the cyclical universe is no longer as viable, because it really doesn't seem like the universe can slow down and go the other way unless dark energy magically turns off or suddenly disappears. And we don't expect dark energy to suddenly disappear. It currently counts for like 70% of the universe, of the energy of the universe. We don't know of any mechanism that would make dark energy just disappear, which means this idea of a collapsing universe, unfortunately, is not favored by the data. Okay, so if we're not going to have this very nice cyclical big crunch, big bang cycle, what are we going to have? So that very much depends on what's happening with dark energy. So there are two scenarios we can consider. Option one is that dark energy carries on expanding with the same strength that it has right now. The same overall expansion rate, gradually accelerating, but in this continuous way. Option number two is dark energy is actually growing in strength, and the acceleration will increase and get faster and faster and faster and faster, and gradually increase more and more and more. And we'd end up with a huge exponential expansion that keeps getting bigger and bigger and more intense, more exponentially exponential. So let's talk about these two scenarios. The first one is known as the heat death or the big freeze. Now, in this case, the universe continues doing what it's doing now. Everything moves away from everything else. Everything gradually drifts apart. The universe expands. This expansion accelerates. Everything moves away from everything else. What is this going to lead to? Eventually, everything will be so far away from everything else that there can be no exchange of energy, no exchange of information, no exchange of heat. You'd look, if we were still here, you'd look up in the night sky and see a completely dark, empty, desolate cosmos, because the closest star to us would be so far away that its light would never have time to reach us. galaxies would never see each other because they'd be so far away from each other that the light could not do anything. Now, this is known as the Big Freeze or the heat death because as the universe expands, it cools down. Once everything is very cold and very far away from each other, you literally have nothing that can happen in the universe. So the universe would end up as a cold, empty, desolate wasteland with nothing happening. And this is either the heat death, the death of heat, or the Big Freeze, because literally the universe freezes over. It is everything has been pushed far away from everything else. So this is if dark energy continues behaving the way it is currently. Heat death of the universe, empty sky, you will never see anything when you look up. You'd think you're alone in the universe, but you wouldn't even have a sun to sustain you, so you wouldn't even know that you're alone in the universe. Fun. Heat death, fun scenario. Let's go to the other idea. What if dark energy increases? What if dark energy starts expanding even quicker? If dark energy is stronger than it is now? Well, then the expansion becomes so intense that not only does it start pulling things away from each other, but it starts pulling atoms away from each other. And then it starts pulling everything away from everything else. All of the protons get pulled away from the neutrons. Basically, everything gets ripped apart at the seams. The universe is torn apart. And this is what is known as the Big Rip, where the universe is literally ripped apart. This means that there will be no planets, there will be no stars, there will be no galaxies, there would be no atoms. You would just have the fundamental particles, the basic building blocks of everything, scattered throughout the universe, too far away to talk to each other. So this is kind of like the Big Freeze, but even extra, because not only does everything freezes after it's been torn to shreds. So that's fun. So possible scenarios so far. A nice calm cyclical collapse and then expansion, collapse, and then expansion, calm. Nothing would calm about collapsing, but calm. Or so we could have the big crunch where we collapse upon ourselves and then potentially expand again. This one is disfavored by the data. We could have a Big Freeze or the heat death where the universe ends up a cold, desolate, empty, dead wasteland. Or we could have the Big Rip where the universe is torn apart at its seams and there is literally no structure. We have these three scenarios. One of them is disfavored, the other two, we actually don't have enough information about dark energy to know if we're heading for a Big Freeze or a Big Rip. Like, we really do not know. Either of these could happen. Right now, the data seems to point a bit more towards a Big Freeze than a Big Rip, but not by much. So as we get more data in the next few years, we'll be able to answer that question a bit better. So these are all kind of terrifying ways the universe could end. But there is one that is my favorite that I haven't yet talked about. As Scott just put here on the comments, don't forget vacuum decay, as if I could forget vacuum decay. So the Big Freeze, the Big Rip are quite scary, but we're talking about something that would happen billions of years into the future. So, the human race wouldn't be around by then. It's not something that is going to happen tomorrow. So it's not something we really need to worry about. But there is a way that the universe could end right now, or tomorrow, or in a few minutes, or never. And this is the vacuum decay. So in the case of vacuum decay, what we have is, a couple of things to know about the universe. First of all, the universe likes being in its lowest energy state. This is something that we can think about very easily. If you put a ball on the top of a hill, it's quite likely that the ball is going to roll to the bottom of the hill because then it's in its lowest energy state. If you balance a pen very carefully like that and actually balance it, eventually the pen will fall down because being on the ground is more stable than being in this position. I can keep the pen there for apparently less than a second and then it's going to fall down, because eventually it is going to reach its lowest energy state. Here, there is some potential energy. It has a potential of falling. Here, there is no potential energy, assuming it's fallen on the surface. So the universe likes being in its lowest state. Okay, point number 2. The universe is filled with fields. Now, fields are something that has a value everywhere in space. So for an example, when we talk about the electromagnetic particles, there is actually the electromagnetic field that is everywhere. And these fields are basically what tell particles how to interact with each other. These are everywhere. The universe is filled with fields, and these set the fundamental laws with which particles can behave, can talk to each other, can interact, can do things. Okay, so following on from the universe, everything wants to be in the lowest state. All of these fields also want to be in their lowest state. So let's imagine I'm going to draw a field here. And apparently I've already used that one for sketches, so let's use this one now for sketches. It's funny going back and looking at the sketches that I've made previous weeks and finding random stuff. Okay, so let's imagine I'm just going to draw something here that is a potential and a field. So let's just start here like this. Right, let's imagine here we have a potential and here we have a field. So this is a plot of potential and field. And your potential starts here and has this minimum. So if you put a ball at the top, this ball is going to roll down to its minimum, right? Ball starts up here, ball is going to roll down to here. But what if there is a second minimum? What if this is what we call a false minimum? And your potential, let me just draw the ball here. What if your potential actually looks like this? So the ball started at the top here. It has rolled down to this part here where it's a bit stable. You know, it's not going to roll over there. It doesn't have enough energy. But there is this minimum down here. So this is what we would call a false minimum, and this is the true minimum. So what would happen if this ball could suddenly jump over here? So it can't go up because it doesn't have enough energy. But we know that in the quantum world, everything is possible. And if you wait long enough, you can have quantum tunneling. So what happens with quantum tunneling? The ball can basically find a way to tunnel over to here. Now, this has a very, 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 very small probability of happening. But if you wait long enough, it might. So the ball could go from up here to here, stays here, and then it could tunnel. Once it gets here, it's going to plummet down here. Ball has reached we call this a metastable state because it looks like it's stable, but it's actually not. And by some random quantum fluctuation, it could go here, and then it would crash down to the bottom to its true minima. So it's in a false minima, could crash to its true minima. So if this were to happen, let's imagine we have a field in the universe that is in a metastable state, that is in its false minimum. Now, if this false minimum field at some point has a random quantum fluctuation and tunnels to its lowest state, it will plummet down there. And it will change the entire interaction, the entire rules of the game of this field, because it goes from being in one energy state to being in another one. You know, the same as when I'm balancing a pen here, I should close that before I draw myself, when I'm balancing the pen here, the things you expect this pen to do are very different than when the pen is on the ground. Right here, it has a lot of things it could do. It can go in any direction, it can rotate. Once it's here, there's not much it can do. The rules of the game have changed. So if we have a field that is in a metastable state, it could tunnel to a new state. So let's imagine there's a field in the universe in the metastable state. And at some point, somewhere in the universe, this field has a random fluctuation and finds its new minima. Now, this information is going to spread. Once part of the field has reached a new minima, the whole field is going to crash down everywhere in the universe. So where this happens, you're going to get an expanding bubble. Inside this bubble, you have the new laws of physics. You have the new field, you have the true minimum. Outside, you still have the false minimum, the universe as we know it. But this bubble is going to start expanding at the speed of light. As it does so, it will erase everything in its path. It doesn't just rip things apart or set them on fire, it deletes them. It resets the laws of physics, it resets the playing field. So we don't know what a universe would look like inside this bubble, but it would be very different to the universe outside. And the universe outside and the universe inside cannot coexist. As this ball expands, it's going to create a shock wave in front of it, so it's going to heat up particles. So it's actually going to be an expanding fireball. So inside this fireball, you have the new vacuum. Outside, you have the old vacuum. And this is going to expand at the speed of light, taking out everything in its path. It is an expanding ball of death. And this is what is known as a vacuum decay, because the vacuum decays from its metastable state to its true stable state to its true minima. And this would expand. So, big question, are there any fields that are in a metastable state? I'm so glad you asked. The answer is maybe. So one field that we know that is everywhere in the universe is the Higgs field. The Higgs field is what gives everything mass. is what allows particles to have mass. You can kind of think of it being like a thick treacle that adds a drag that makes it hard for particles to move, and this difficulty to move is what we call mass. Now, the Higgs might be in a metastable state. It might not, but it might be that this here that I drew is exactly what the Higgs potential looks like. And if this is the case, we are here. If the Higgs looks like this, we are probably here, which means at some point, at any point, there could be a quantum fluctuation, just a random fluctuation in the universe, and the Higgs field would suddenly tunnel to its true vacuum and pull the rest of the universe down with it. Now, if this happens, we would not see it coming. We would have no warning, because this bubble would be traveling at the speed of light, this expanding bubble of death. The first we would see of it would be when it hits us. And as soon as it hits you, you will blink out of existence. There is no option, no, oh, maybe I can survive this firewall, maybe I can survive in the vacuum. You will not. If the Higgs tunnels to its lowest state, it will create an expanding bubble. This bubble will expand at the speed of light and basically hit everything in its path. This might already have happened. It could have happened here, it could have happened the other side of the universe, could have happened close to the sun. We do not know. We would have no way of knowing. We could already be on the path to destruction and we would not know it. Now, caveats, as Paul is mentioning here in the comments, if our universe is expanding exponentially, we know the universe is expanding, we could outrun a vacuum decay event. Yes, if vacuum decay happens only in one place in the universe, and we are so far away that, that place doesn't even send us light, the vacuum would never reach us because we'd outrun it with the expansion of the universe. But if this happens somewhere in the universe, what is stopping it from happening elsewhere in the universe? Now, usually when we do these, putting our physics in a box and seeing what happens when we do this with vacuum decay, multiple bubbles appear and these bubbles expand and yeah, so the universe could literally stop existing at any point and there's literally nothing we could do about it. And this is known as the vacuum decay, and this is my favorite end of the universe scenario. Why? Why is this my favorite when it's terrifying? To me, it puts things in perspective, The universe could literally end at any moment and there's nothing we can do about it. So in the grand scheme of things, does a missed deadline matter? Does the fact that you're feeling sad today matter? The universe might end at any moment. Enjoy it while you can. So I find it very, very positive to think about the vacuum decay, but I know it is very terrifying. So just a few caveats. We are not sure for sure. We are not completely sure if the Higgs is in a metastable state. If it is, the chance of it doing this tunneling is very, 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 very small. You need to wait a very long time for this to happen. That said, the universe is very big and we've been around for 13 billion years, almost 14 billion years. How many years do we wait before this happens? So I don't think we need to be worried about vacuum decay happening tomorrow, but there is a small chance of this happening. And if it happens somewhere in the universe, these bubbles will expand and eventually potentially reach us, unless it's so far away that we can outrun it. And I love this because the vacuum decay is like the ultimate reset button of the universe. Like, I've decided I don't like the laws of physics anymore. Reset, new laws of physics, new vacuum, good luck. So there are many possible ways the universe could end. The cyclical one of the Big Crunch doesn't really seem to be compatible with the latest data. We could have the universe tearing itself apart at its seams in a big rip where everything is torn to shreds. We could have the heat death or the big freeze where the universe ends up a cold, desolate, empty wasteland. Or we could have a vacuum decay where the universe just stops existing at any given time. All very happy end of the universe scenarios, or there could be something else that we haven't even thought of yet because the universe is weird and confusing and it's full of things that we don't yet know. So maybe none of our theories are correct and maybe the universe will end in a completely different way. Fun fact, this idea of this vacuum and having a field that's like this is something that might already have happened in the early universe. There might have been a time where the universe did this, where it went from one vacuum to another, where we had these bubbles of the new laws of physics, the new vacuum expanding and slowly taking over the universe. if this did happen in the very, very early universe, we're talking like a fraction of a second after the end of inflation. If this did happen, these bubbles collide and produce sound waves. I mentioned there are these shock waves in front of them. So all of this is very, very messy. And what this does is it leaves ripples in space-time itself. So if there was such a bubble expansion in the very early universe, going from a false vacuum to a true vacuum, this could have left tiny, tiny ripples, which we call gravitational waves. We're talking about tiny ripples in the fabric of the cosmos produced 14 billion years ago by a false vacuum decay. This is what I get to work on right now. And the very cool thing is that in 10 years-ish, the European Space Agency is launching a mission known as LISA, the Laser Interferometer Space Antenna. LISA is going to look for gravitational waves coming from massive black holes smashing together, from objects falling into supermassive black holes, but also LISA is going to search for the ripples that might have been produced in the very early universe by a false vacuum decay. And this is what I work on, and this is amazing. Hey, thanks for stopping by, David. Great to see you. Enjoy the rest of your evening. So it's really cool to think about that. I'm talking now about a potential way the universe could end, but the same physics could have happened in the very early universe. And if so, it could have left ripples in the fabric of the cosmos that we might see in 10 years when we launch a mission. So this project that I mentioned that keeps getting delayed and delayed and delayed, we're asking the question of, is LISA actually going to find these things? And we'll see. But I'm optimistic. I am always going to be an optimist. So yeah, we don't know how the universe is going to end. There's a lot of cool different physics that could happen. There's a lot of different scenarios. All of them have a lot of cool physics behind them. One of my personal favorites is vacuum decay. The universe could disappear at any point. But the same physics that we would use to describe this vacuum death of the universe, this vacuum decay, can be applied to the very, very early universe. And this is something that maybe we can study in the next 10 to 20 years. And that is very, very, very cool. So thank you for the question about the death of the universe. I love that question. It is such a fun topic to talk about. And I did a whole stream about the death of the universe at some point. So I'm just going to take this chance to plug somebody else's book, who is not me. There is a book by Katie Mack called The End of Everything, Astrophysically Speaking. It is a very cool outreach book. It's a very cool science communication book. And it basically talks about all the ways the universe can end. So what I just did in 20 minutes, but done in a whole book. It is very fun to read. I highly recommend it. It's The End of Everything, Astrophysically Speaking by Katie Mack. And I did actually have Katie Mack on Cup of Cosmology about 18 months ago, 2 years ago, I think it was, where we did a whole episode about how the universe is going to end. The episode is in the highlights. If you go to Cup of Cosmology, the YouTube channel, there is a playlist I've made called Highlights, which is my favorite episodes. There's like 20 there, but one of them is the death of the universe, where you can get the full 1 hour version of this talk with Katie. And it was a very cool episode. Okay, we have reached 1 hour and 4 minutes. Got caught up in the death of the universe, not literally. So we went a bit over today. So thank you everyone for the questions. It's been really fun. Some days I cover like 20 questions and some days I cover 2 or 3 questions. And today we spent quite a while talking about self-interacting dark matter and quite a while on the death of the universe, with a random tangent in the middle about unionizing. And I like both formats. When we do 20 questions, it's really fun because it's quick fire and there's a lot of topics. But when I get to go in depth in topics like the heat death or self-interacting dark matter, it's also fun. So I like both formats. Thank you for the questions. Everyone who joined, this was really, really cool. As I said earlier, next Sunday there will not be a Cup of Cosmology because I will be on holiday. I am traveling. Basically, now that the stream is done, I'm going to finish packing, and tomorrow I go on holiday. I have to work in the morning, and then I go on holiday, which I'm really looking forward to. So next Sunday, there will not be a Cup of Cosmology. Next Cup of Cosmology will be in 2 weeks on the 8th of April. Already April, wow. 8th of April, where I might do a special theme of ups and downs of academia. We'll see, but that is going to happen soon. So yeah, I hope you all join again in 2 weeks. Reminder that we are changing our clocks next week. So I know some of you have been out of sync for 3 weeks because you already changed your clocks and we haven't yet. We change our clocks next week. So by the time I'm back on in April, I'll be back to usual schedule, or like it's 8 p.m. Finland time in summer, which is my usual times. As always, there is a time zone converter on cupofcosmology.com, so you can watch it there. You can check on cupofcosmology.com to figure out when the next stream is going to be in your own time zone. If you haven't done so yet, subscribe to the channel, and then you will get notified 30 minutes before I go live, so then you can't miss it. Okay, thank you everyone for joining. This has been great fun. Cup of Cosmology will be back in 2 weeks. I hope to see you all again then, and I hope in the meantime you'll stay safe and take care of each other.